Hey everyone. So today is lesson 3, and this is a big one. We are going to introduce the concept of the unit circle. Now, really, we're just going to marry a lot of stuff that we've already talked about together, okay? This is going to be all about angles and standard position, and then we have to throw in a few special triangles. Now, special triangles you would have learned last year. I am going to quickly go over them again this year, just in case you don't remember. But we're going to put all that together and form the unit circle. So this is going to be one that a video that you want to pause a lot on. You might even want to watch a few of these sections a couple of times just to really help you as you try to build the unit circle. I will say right off the bat, especially for those of you who have tutors, I'm not a big fan of you trying to memorize the unit circle, okay? I'm not a big fan of you just trying to stare at something and get a photographic memory going and just write it all down, okay? That's never the purpose of the unit circle. The purpose of the unit circle is to build it. It's to understand how it works, how it functions, and if you can build it, you will not make mistakes in your memory. Okay, because now you understand how it works. And so that's what I want you to think of right from the beginning. Don't try and memorize it, try to understand it and build it with an understanding instead, okay? Okay, so on the grid, draw a right triangle in quadrant 1 with a vertex on the origin. Easy peasy, there I go, right triangle in quadrant 1, vertex on the origin. Now, I'm gonna call the base of that triangle X, I'm gonna call the height of that triangle Y, and I'm going to call the hypotenuse R, and that should sound familiar to you because I was sort of doing that with angles in standard position yesterday. So if I call, and this may sound funny to you, but it's a very important thought. If I'm calling the base of this triangle X, and I'm calling the height of this triangle Y, then right on the edge, this point right there, the way to get to that point has to be X comma Y, because I had to move over X and up Y. Okay, so the coordinate point at the very tip of that triangle is X comma Y. Okay, now what would happen if we took that point, the X comma Y, on the end of the hypotenuse and rotated it 360 degrees? What would we end up with? Well, if I took this and rotated it 360 degrees, I would end up with a really bad drawing of a circle. Okay, but that's okay. What I want you to notice is that XY gets rotated all along the edge here. So think about this triangle I drew here. Why can't I have drawn it right there? Right? Or why can't I have drawn it right here? Whoops, don't go beyond the circle. That's going to annoy me. I'm going to erase that for you. Why can't I have drawn it here like that? Or why can't I have drawn it here like that? Okay, what I want you to understand is this circle that we've drawn is really a combination of all these little triangles all the way around. Okay, now, if you'd like a better drawing of a circle, I do have a better drawing of a circle for you. So what would we end up with? We'd end up with a circle and it would look like that. Okay, using the Pythagorean theorem, can we now develop an equation for the circle? Well, this is the conversation I just kind of started when I was starting to draw all those triangles. No matter where I draw those triangles, I could use the Pythagorean theorem and I could say that x squared plus y squared equals r squared, right? So I could draw a triangle right here. And this would now be x, and this would now be my y, and this would now be r. But the relationship in that triangle is still x squared plus y squared equals r squared. And so, and that's still a point out here. I want to say that one more time too. So that's still the point out here, whatever x comma y is, right? And so x comma y can represent any point on the outer edge of that circle. But at any point on the outer edge of that circle, I have a Pythagorean relationship there where I can have a triangle and I can say x squared plus y squared equals r squared. So guess what? X squared plus y squared equals r squared is actually the equation of a circle. Okay. Now, just stop and think about that for a sec, because I know it's a little mind-blowing because it's been the Pythagorean theorem all your life. But it is the Pythagorean theorem. But in the context of a circle, this actually will get me to any coordinate point on the outer edge of that circle, where x comma y is a point on the circle and r is the radius of the circle. That's why I was using r yesterday. It wasn't because it was my favorite letter, like I told you. It's because it's the radius of the circle. So for instance, if I wanted the equation of a circle where the center of the circle is at 0, 0, and I have a radius of 4, then I would be looking at this equation. I'd say, okay, well, that's x squared plus y squared equals 16, because 4 squared is 16. Okay. You can also imagine, because we've already done transformations, that I could slide this right, left, up, down just by replacing x with x minus 2 or replacing y with y plus 3. Okay, that gets into a whole other unit called conics, which is not taught in 30-1 anymore, but they're very exciting. And actually, you already know most of what you would need to know for conics, because it's really just transformations on this circle. You can imagine if I stretch x, but I don't stretch y, I don't have a circle anymore. I have an oval or an ellipse. Okay. Anyway, we won't get into that. That's for another conversation. So remember, although x and y are the length and widths of the triangle that you see, they also represent any point on the outer edge of that circle, which means we could find a triangle based on any point to get a value for x and y using the equation we just wrote. And so the first part of this whole unit circle conversation is just to be able to get comfortable using that equation. Now, what should we call the hypotenuse of that triangle? We've already said this, it's the radius. I got a little excited and I got ahead of my slide here. Okay. Okay. So if the hypotenuse was length 1, remember I just gave you an example where the radius was 4. So we said it was x squared plus y squared equals 16. Now we're saying the hypotenuse or the radius is 1. How does our equation adjust? Well, now it's going to be x squared plus y squared equals 1, because 1 squared is 1. That fella, x squared plus y squared equals 1, is the equation of the unit circle. Okay, a unit circle is a circle with a center at the origin and a radius of 1. Center at the origin and a radius of 1. Okay. All right. So first question that we want to look at, determine the missing y coordinate for each point on the unit circle. Now we're going to have some fun with this. We're going to do this without a calculator. So if you have a calculator sitting beside you, put it away. My point is, we shut down when we have fractions. We get super scared. It's not as scary as it looks. Okay. What we're going to do is we're just going to plug in -4/5 into my unit circle equation. So x squared plus y squared equals 1. So I've got -4/5 squared plus y squared equals 1. Okay, well, I have to square -4/5. When I square a fraction, I just square the square the top, square the bottom. Negative squared is going to be positive, so that's going to be 16/25. Okay, easy peasy. I don't need a calculator, just tell me 16/25. Now, I have to subtract 16/25 from both sides. Again, I don't need a calculator, neither do you. I'm just going to call my 1 25/25. Then I have a common denominator, right? And I can do that in my head, because now I'm going to go 25 minus 16/25. Well, what is 25 minus 16? So y squared is 9/25. Do you follow what I did there? 25 minus 16 is 9. Y squared is 9/25. Now I'm going to square root it to get y out by itself. So that becomes plus or minus 3/5. Okay, so there's two options for y right now until I look at the rest of the information that I was given. I was also told that I was in quadrant 2. So if I'm in quadrant 2, which would be right here, right? Where is y going to be positive or negative? Y is going to be positive. Okay, so my value is negative 4 over 5, comma, 3 over 5. Okay, next up, I just want to erase that ink, sorry. Okay, next up, same question, but now it's going to be point B. I've got 3 over 10, comma, y, and I'm in quadrant 4. Pause me and do it yourself. See if you can do it without a calculator, because that'd be fun. That'd be fun. Okay, so I said 3 over 10 squared plus y squared equals 1. 3 over 10 squared is 9 over 100. I just square the top, square the bottom. I'm going to call my 1 100 over 100, so I have a common denominator. So I'll go 100 minus 9, which is 91 over 100. Everybody with me? Okay, now I have to square root. So it's going to be plus or minus when I square root. I don't know the square root of 91, so I'll leave that as root 91. But I do know the square root of 100, so that'll be 10. So y is plus or minus root 91 over 10. And then I have to decide what quadrant I'm in. So I'm in quadrant 4, and y is negative in quadrant 4. So my final answer will be 3 over 10, comma, negative root 91 over 10. Okay, which of these points are on the unit circle, and how do you know? Well, if they want to be on the unit circle, they have to work in the equation. So remember, my equation is x squared plus y squared equals 1. So if I plugged in 0.6 in for x and 0.4 in for y, and into that equation, does it equal 1? That's what I want you to do, okay? So check each one of the 4. Pause me for a sec. You should have gotten 2 that worked, the 0.6, 0.8, as well as the negative 0.8, negative 0.6. Both of those would have worked, okay? And again, the way we found that out is we plugged them into the equation, and it actually gave me a true statement. If you're doing it like a verification, you would have gotten 1 equals 1 at the end of your verification. Okay, so angle theta in standard position intersects the unit circle at 1 over 3, comma, k, where tan of theta is greater than 0. Determine the measure of angle theta to the nearest degree. So we've already talked about questions like this today. The difference here, though, is I've taken you just a little bit deeper in your level of understanding. It's just slightly more complex because we didn't outright say, hey, you're in quadrant whatever. But we know that tan of theta is greater than 0, which means tan of theta is positive. Well, think about the CAST rule. If tan of theta is positive, I have to be in quadrant 1 or in quadrant 3. Okay, I got to be there. But then if you look at the point that you were given, the x value is positive in that point. So that immediately says, okay, you have to be in quadrant 1 right now, because that's the only thing that makes all of it fit. Okay, that will give me my positive x value, and it would give me my positive tan ratio. Okay, so I know I have to be in quadrant 1 for this guy. All right, so I'm going to use my unit circle formula. X squared plus y squared equals 1. I plugged in 1/3 for x. I know 1/3 squared is 1/9. I will have to subtract 1/9 from both sides. Again, to do that, we're not going to use a calculator here because we can do this without a calculator. I'm just going to call 1 9 over 9. So I've got 9 over 9 minus 1 over 9, and that gives me 8 over 9. So y squared equals 8 over 9. I want to square root it. The square root of 8 would be 2 root 2 when simplified, right? Root 8 is 4 times 2. Root of 4 is 2. So 2 root 2. And then the root of 9 is 3. So we'd be looking at a y value of plus or minus 2 root 2 over 3. But then based on the conversation we just had, we need to take the positive version of that. So the point that I have right now is 1/3, comma, 2 root 2 over 3. Great. But we were asked for the measure of theta. So again, I've taken you just a little bit deeper than those first couple of questions that I asked you, where it was just find the missing point. Now that I have this, I want to use this to figure out theta. Well, if I have a triangle, we did this yesterday, if I have a triangle and I know the base of my triangle is 1/3 and the height of my triangle is 2 root 2 over 3, tan is opposite over adjacent. It ends up being the height over the base. Do you remember talking about that yesterday? So that means that I'm looking at 2 root 2 over 3 divided by 1 over 3. Now, when I'm dividing fractions that have a common denominator already, I just have to divide the numerators. So essentially that means the tan ratio here is 2 root 2 over 1, or is just 2 root 2. Okay, so tan of theta is y over x, which ends up being 2 root 2. Now, knowing that tan of theta is 2 root 2, I will arctan it to figure out what my angle for theta is. So, and then I was asked to round to the nearest degree. So if I arctan 2 root 2 and round to the nearest degree, I'd get an answer for theta of 71 degrees. Okay, so now we're going to have a quick little conversation around special triangles. Two special triangles that you learned in grade 11, a 45, 45, 90 degree triangle and a 30, 60, 90 degree triangle. I'm going to build them like you've never built a special triangle before, just to show you that, again, this is not something you have to memorize. If this is something you forget, you just build one from scratch. It's going to take you 30 seconds on a test to build a special triangle and make sure you have it right. I would much rather you take those 30 seconds to build something than go home and try to memorize it and end up memorizing it wrong, because that messes everything up. Okay, so their ratios are 1, 1 root 2 and 1 root 3, 2, but I want to show you where those come from. Okay, so let's start with the 45, 45, 90 degree triangle, which is this guy here. Okay, when I go to establish a ratio, I always go to the smallest angle, and opposite the smallest angle, I'm going to call that a 1. I'm going to establish that as my basis, right? Every other 45, 45, 90 degree triangle is just going to be an enlargement or a reduction of the one I'm currently doing. So you just take the smallest angle, opposite the smallest angle, you call it a 1. Now, this guy's special, like my mama told me I was, because I have two 45 degree angles. If I call opposite one 45 degree angle 1, I have to call opposite the other 45 degree angle 1 as well, because the angles are the same, and that's a hypotenuse, or that's a isosceles triangle. Too many words going on in my head at the same time. Okay, now I actually have two sides of the three sides that I need. It's also a right triangle, so I can Pythagorean my way to the hypotenuse. So 1 squared plus 1 squared is 2. The hypotenuse there is root 2. That's where that 1, 1 root 2 ratio comes from. Okay, now in the 30, 60, 90 degree triangle, I want you to notice that your eyesight should tell you this is not a 30, 60, 90 degree triangle. What I'm actually starting you with is a equilateral triangle. An equilateral triangle is a 60, 60, 60 degree triangle. Okay, but what's special about an equilateral is all the sides are the same. Okay, and when I cut this in half, like that, I end up with a 90 degree triangle, and that's half of 60, so that becomes 30. And look, now that's one side is 30, 60, 90. So that's where I'm going to get my 30, 60, 90 degree triangle from. Okay, like that. So now I'm going to, just like I did with the other triangle, I'm going to take the smallest angle, and opposite the smallest angle, I'm going to call that 30 degrees. Okay, sorry, man, opposite the smallest angle, I'm going to call that a 1. The smallest angle is 30 degrees. Okay. If you ever see glowing mistakes in these videos that I don't catch, you should email me and let me know so I can redo that section. Okay, so opposite 30, I'm going to call 1. So I'm going to stick a 1 right here. Now, here's the next part that I need you to see. Remember that I'm doing this inside a equilateral triangle, right? So if this guy here I've established as 1, that's half of the equilateral triangle. So now if I wanted the whole equilateral triangle, you'd want to tell me that that's 2, which means that's 2, which means that's 2. Okay? So now I've got the 1, I've got the 2, I can Pythag my way to the height. 2 squared minus 1 squared this time, right? Because I'm not solving for the hypotenuse. So 2 squared is 4, minus 1 squared would be 3. And so that would be root 3 for the height. Okay? Root 3 for the height. Okay, so why do we care about any of this? Well, there's a lot of reasons we care about this. And we're just going to kind of build it slowly here for a sec. First, what is the exact value of the sine of 60? Well, you know that sine is opposite over hypotenuse. So you can now take a look at sine of 60 and go root 3 over 2. Okay. Your calculator won't do that for you. Well, it won't do that for you on a test. If you have the new Casios, it will do that for you. But remember that when you write a test, I shut that feature off on your test. So you do need to know how to do this still. So that's important though. This whole root 3 over 2 is sine of 60 because your calculator, when you put sine of 60 in your calculator, you get 0.8660. That's a rounded value. It's not an exact value. And you guys know by now, being in 30-1, an exact value is so much more powerful than some rounded decimal, okay? And so this allows us to get a whole schwack of trigonometric trigonometric functions, ratios in exact value, okay? You can tell me now that the sine of 60 is root 3 over 2. You can tell me now that the sine of 30 is 1/2. You can tell me now that the tan of 60 is root 3. You can tell me now that the tan of 90, or of 30, sorry, the tan of 30 is 1 over root 3, okay? You can tell me that the sine of 45 is root 2 over 2 if I was rationalizing, or 1 over root 2 if I wasn't rationalizing, okay? Now, you might just want to rewind, go back to the 10 seconds, 20 seconds, however long that took, and listen to those statements again. Make sure you're seeing how I'm reading all that information off of the triangle, okay? In our unit circle, our radius, or the hypotenuse, is 1. How does this affect the side lengths of these triangles? Okay, so spoiler alert, what I'm about to do with the unit circle is I'm going to pluck these triangles inside the unit circle, okay? So my hypotenuse, right here, I'm going to throw inside a unit circle, okay? So but the problem with that is, sorry, I was trying to get ink on at the same time. The problem with that is this is not the proper radius. The radius is supposed to be 1. Root 2 is 1.4. That's too big. This is not going to fit inside my unit circle. I want to shrink this down now so that that point right there is on the outer edge of my circle. Like, whatever, that was really bad drawing, but you, like, that would be the outer edge of my circle, okay? And then the like, trying to show you something like that, okay? Okay, well, how do I reduce that? I'll divide everything by root 2. Yeah? Root 2 divided by root 2 is 1, so that's totally cool. So if I divide everything by root 2, divide by root 2, divide by root 2, divide by root 2, because I did it to everything, I essentially just shrunk the triangle, okay? And so that ends up with 1. And then root 2 over root 2 when I rationalize. Now, I do want to have a quick conversation around rationalization. In 20-1, that was forced. You can never have a radical on the bottom of a fraction. In 30-1, it's not forced like that. You can write it in rationalized form, or you can write it in non-rationalized form. It doesn't matter. Unless the question specifically says write in rationalized form, either one would be accepted, okay? Okay, so now that would fit in a unit circle. The next thing I want to do is to go over here and try and make this guy fit into a unit circle. Again, my hypotenuse is 2. That's too big because in the unit circle, I want my hypotenuse to be 1 because the hypotenuse is the radius in the unit circle. Okay, just divide everything by 2 then. 2 divided by 2 would give me 1, so that's great. Then I'd have 1 over 2, and I'd have root 3 over 2. Okay? All right, so now what we're going to do is we're going to take a look at just the first quadrant of the unit circle and begin to see how these triangles fit into the first quadrant. Really, once you understand how I'm doing the first quadrant, the rest of the unit circle is not complicated, okay? Because it's just repeating this over and thinking about who's negative and who's positive. Okay, so here's the first quadrant of the unit circle. What I want us to do is to walk through, our job will be, we want to look at what the angles are in both degrees and radians. And then we also want to get the coordinate pair for the edge coordinate at the end of each of these lines. Okay, so this is 0. Hoping you're comfortable with that. This would be 90 degrees. Okay, my red line here is a 45-degree angle, and then my blue lines are 30-degree angles. So this one would be 30, and this one would be 60. Okay, so we'll start just by putting those in. Now, the next thing I want to do is put in the radian measure for these. And radian measure is actually going to be super easy to deal with when we actually get to the whole circle. I'm going to show you, all you have to do is count to 8 and count to 12. If you are able to count to 8 and you are able to count to 12, you're going to have no problem with the radians, okay? But right now, until I can show you that whole thing, just convert these. So 30 degrees converted into radians, 0 degrees, well, 0 is 0. 30 would be pi over 6. 45 would be pi over 4, 60 would be pi over 3, 90 would be pi over 2. Okay, so I didn't say this, but 0 is also 360, right? If I have gone the full circle, and then for radians, 0 is also 2 pi. Okay, so I have my radian measures in there. Now, coordinate points. Remember that the unit circle is a radius of 1. And the center is at the origin. So I know right away the coordinate point for 0 has to be 1, 0. And the coordinate point for 90 has to be 0, 1. Okay. Oh, sorry. Let me take that away for you for a sec. I thought my slide would have gone to 0, 1 first. So that guy's 0, 1. I'll show you that in a minute. Okay, so let's deal with that 30 degrees. And actually, what I want you to hear is we've already dealt with that 30 degrees, because what I want you to think about is I want you to think about the triangle that I just got you to do. So here's that outer edge of the circle, right? If this is 30 degrees and this is 90 degrees, this is 60 degrees. So I have a special triangle. I have 30, 60, 90 degrees. Okay. Well, we've already established that the ratios for that guy was, well, actually, I'm just going to build it again, okay? I changed my mind. I've already showed you how to make it fit on the unit circle, right? But let's pretend you forgot that for a sec. We're just going to review it one more time. So the ratio is, opposite the 30 would be 1, right? Opposite the 60 was root 3, and then my hypotenuse was 2, okay? But that doesn't fit in the unit circle, so now I divide everything by 2. So that it does fit in the unit circle, okay? So take a look. Right off the bat, I know that this guy, that coordinate point right there has to be over root 3 over 2, up 1/2. Over root 3 over 2, up 1/2, okay? Now, this tells me a whole whack of stuff. Let me just put that coordinate pair there for a second so that you can see it on the slide. I know that I'm kind of small, so when I write on the board, if it gets too intricate, it's hard to read. So I'll try and keep the stuff on the slide for now. Very, very important, the conversation I want to have right now. 2 things just happened. Number 1, you have been able to tell me what the coordinate point, the exact value coordinate point right there is. Okay, so it's on the edge of the circle with a 30-degree rotational angle. But here's number 2. Think back to this triangle for a sec, okay? If this was 30 and this was 60 and this was 90, okay? And then this was root 3 over 2 and this was 1/2. If I now asked you to get me the sine of 30, okay? The sine of 30 is opposite over hypotenuse, or your y value over your r value, or just your y value, because your r value is 1. This only works in the unit circle, okay? It only works in the unit circle because the radius is 1. So y over 1 is just y, which means when we are doing these coordinate points, the y value ends up being the sine of that angle. And for the exact same conversation, the cos value, well, cos would be adjacent over hypotenuse, or your x over 1, okay? Well, x over 1 is just x, so your cos value ends up being the x value of your coordinate. Now, go test that out, because I've already written the coordinate for 0 down here. Go cos of 0 and you should get 1, and go sine of 0 and you should get 0. Okay, so every point that I'm about to draw here is cos of theta, comma, sine of theta. Cos comes first, just remember Calgary Stampede, C, then S, okay? Cos of theta, sine of theta. Calgary Stampede, you see what I'm saying? Okay, every coordinate point is cos of theta, comma, sine of theta. Okay, so now let's have the same conversation for 45 degrees. Well, the 45 degrees, if I was to drop that perpendicular, I'd have 45, 45, 90. This ended up being 1. This ended up being root 2 over 2. And this ended up being root 2 over 2. So the coordinate point was root 2 over 2, comma, root 2 over 2. Again, if you would like to not rationalize that, if you would like to call that 1 over root 2, comma, 1 over root 2, totally fine. Then pi over 3 and 60 degrees, what I need you to see is that's just the flipped version of this, right? The 60 would be here, the 30 would be here, which means the 1/2 would be down here, and the root 3 over 2 would be there. So they actually just flip. So that becomes 1/2, comma, root 3 over 2. Okay, so now we come to our last point, the angle in standard position that would form a 90-degree angle or a pi over 2 radian. Remember, those are the same thing. The coordinate point there, remember that your unit circle has a radius of 1. So that point is going to be 0, 1. Okay, now remember, every point that we see here is in the form cos of theta, comma, sine of theta. So when you're looking at that point, 0, 1, you're looking at the knowledge that cos of pi over 2 is 0. The ratio for the cos of pi over 2 is 0. The ratio for the sine of pi over 2 is 1. Okay. All right. Now, if we were looking for the sine of 30, we know that it's opposite over hypotenuse, but what is the length of the hypotenuse? So I've already kind of talked about this. That's where I'm getting at that y value. Because it's the opposite over the hypotenuse, it's the y value over the radius in this example. But because the radius is 1, it just becomes the y value, okay? So every point that you see on the unit circle, and I know I haven't shown you the unit circle yet, this is only a quarter of the unit circle, right? We're about to duplicate this in all of the other 3 quadrants, but you can imagine, I think you can imagine, this was actually the worst part. This was the toughest. Duplicating it in the other quadrants actually isn't complicated at all, okay? But for every point we see on the unit circle, the x value is cos of theta, and the y value is sine of theta, okay? Just remember, Calgary Stampede. We never talked about tan of theta yet. Tan of theta is there too. Remember, tan of theta would be opposite over adjacent, and in the context of the unit circle, that would be y over x, right? Well, that means it's sine of theta over cos of theta, the y value divided by the x value. Okay, again, this only works with the unit circle, so don't extend this unless you're in the unit circle. This is when you can do it this way. You will also notice on your formula sheet that there will be a statement up at the top right where they're talking about some of the beginning identities. It will tell you tan of theta equals sine of theta over cos of theta. Okay, so that is another thing that you don't necessarily have to remember. But if you understand how the unit circle is set up, it's really not, it's not a flying leap to remember that. Okay, so not all of these notes here are in your book. They're just me kind of wrapping up, summarizing what we've talked about. So having these two special angles, or sorry, special triangles, that's the 45, 45, 90 degree triangle and the 30, 60, 90 degree triangle, allows us to map coordinates on the unit circle that actually represent the exact values for some of our trigonometric ratios. The other thing I want to make sure I make a point of saying is you have to remember that there's an infinite amount of points on the unit circle, okay? When I'm done building the unit circle, we'll have seen like 16 different points, okay? That's not the only amount of points that are on the unit circle. They just happen to be the prettier points that we have exact value knowledge of, okay? I can pick any random point on the unit circle and figure out the x and y value just by taking the cos of that angle and the sine of that angle and having some sort of a decimal approximation. But what we do when we build the unit circle is we're looking at a certain amount of special points where we can get those ratios an exact value, okay? The coordinates of the points along the unit circle actually become bracket cos of theta comma sine of theta. And then to solve for tan of theta, we take the y value and divide by the x value. Even better, each of these triangles will give us many more angles, and we'll see that when we get into identities. Okay, so here we go. Now, in order to look at the unit circle proper, I think the easiest way, and again, I know I've already said this, lots of teachers are going to tell you, go memorize the unit circle, look for some random pattern, remember that pattern, and just duplicate it. I don't want you to memorize the unit circle. I want you to understand how it works. I want you to understand how it's built, okay? If you understand how it's built, the memorization is not needed. So the way I build a unit circle is I go around 3 times, okay? The first time I go around, I'm just going to look at those quadrantal angles. So I'm just going to be looking at the x-axis and the y-axis. The second time I go around, I'm going to look at my 45-degree lines. And then the third time I go around, I'm going to look at my 30-degree lines. Okay? Okay, so just a reminder of each of the quadrant, who's positive and who's negative. In quadrant 1, I'm positive, positive. Do you know what? For the next couple of minutes, I think it's better to hide myself because I'm going to be in the way of all of the unit circle here. And I don't think you need to see me for this. I think you just need to listen to me. So I'm going to hide myself. There I go. And so now you can see I have that positive, positive there. So positive, positive in the first quadrant, negative, positive in the second quadrant, negative, negative in the third quadrant, and positive, negative in the fourth quadrant. So this first go around, I'm just going to look at the axes, okay? And my goal here is I want to know what the degree measure is, the radian measure is, and what the coordinate pair is, okay? So if we talk about degrees first, we're pretty comfortable that that's 0 and 360. We're pretty comfortable that that guy's 90, that guy's 180 degrees, and that guy's 270 degrees. For radian measure, I think you're getting comfortable with the radian measures for these 4 at least. We know that that's 0 and that's pi. Then we know that this guy will be halfway between that, so that's half pi. And this guy down here will be halfway between 1 and 2, so that will be 3 pi over 2. So I'm going to put those guys in. Okay, and then the coordinate points, we've already discussed the first 2. This guy would be 1, 0. This guy would be 0, 1. If I'm on the other side here, this is -1, 0, and this is 0, -1. Okay, so that was my first round of the unit circle. Remember I said I only need to do this 3 times. That's 3 rounds of the unit circle, okay? Now, the next round of the unit circle is my 45-degree line. So I'm adding in my 45-degree lines. And then when I go around, I'm going to count the axis each time, okay? So essentially, all I have to do is start at 0, start right here, and add 45. So 0 plus 45 is 45. Plus 45 is 90, plus 45 is 135, plus 45 is 180, plus 45 is 225, plus 45 is 270, and then plus 45 is 315, okay? Now, I just want to put on a highlighter so I can show you what I'm about to do. For radian measures, remember I said earlier, all you have to do is be able to count to 8 and to 12, and I want to explain why I'm saying that. So you know that right here is pi, that's 1 pi. So you're asking yourself, how many times do I have to move in order to get to pi? Well, I have to move 1, 2, 3, 4 times. So that means every step I take is pi over 4. So all I have to do is start going 1 pi over 4, 2 pi over 4, 3 pi over 4, all the way up to 8 pi over 4, because 8 pi over 4 would give me 2 pi. So I start here, that's 0 pi over 4, and I already have that. 1 pi over 4, 2 pi over 4 reduces to pi over 2, and it's already there. 3 pi over 4, 4 pi over 4 reduces to pi, and it's already there. 5 pi over 4, 6 pi over 4 reduces to 3 pi over 2, and it's already there. 7 pi over 4, and then 8 pi over 4 reduces to 2 pi. Okay, so you don't have to start memorizing that 45 degrees is pi over 4. You just have to think about it in terms of radians. Remember, I've said a couple of times, I want you to think in radians. Okay, then you don't have to do all these conversions in your head all the time. Okay, now we've already discussed that the point there is root 2 over 2, comma root 2 over 2. And if you want that as 1 over root 2, that's totally fine as well. What I want you to now understand when I go to the next quadrants, I'm just going to put a different color highlighter on for a sec. This guy is still a 45 degree reference angle. Okay, so that's this right here is the same triangle as this right here. The only difference is who's positive and who's negative. So for every one of these red points that I've drawn for you here, the coordinate pair will be root 2 over 2, comma root 2 over 2, except that sometimes x will be negative, sometimes y will be negative. Okay, so in this quadrant, I've got negative x, positive y. In this quadrant, I've got both of them being negative. And in this quadrant, I've got x being positive and y being negative. Okay, and that is the second go around. Okay, remember I said all we have to do is do this 3 times. So the third go around adds in the 30 degree lines. Okay, so let's put those in. And now, again, when I go around this circle for the third time, I'm still going to use the axis. I'm still going to use the y and the x axis, but I'm not using the 45 degree lines right now. Okay, so I have to just skip the red lines in my mind. So I'm just adding 30 each time. I start at 0. 0 plus 30 is 30, plus 30 is 60, plus 30 is 90, and it's already there. Plus 30 is 120, plus 30 is 150, plus 30 is 180, plus 30 is 210, plus 30 is 240, plus 30 is 270, plus 30 is 300, and plus 30 is 330. And then plus 30 one more time would give me back to 360. Okay, so now for the radian measures, I'm going to do the same thing. I'm going to count how many times does it take me to get to pi. Okay, so it takes me 1, 2, 3, 4, 5, 6 moves to get to pi. Okay, that means every move is pi over 6, which means all I have to do is start counting 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, all the way up to 12 pi over 6, and I'm done with radians. You just have to remember that you reduce along the way. So 1 pi over 6, 2 pi over 6 for 60 degrees here, but that's going to reduce to pi over 3. 3 pi over 6, that would reduce to pi over 4. 4 pi over 6 would reduce to 2 pi over 3. 5 pi over 6 doesn't reduce. 6 pi over 6 reduces to pi. 7 pi over 6 doesn't reduce. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. 7 pi over, or sorry, after 10 comes 11. 11 pi over 6 doesn't reduce, and then 12 pi over 6 would reduce to 2 pi. Now I need the coordinate points. Well, we've already discussed these coordinate points, right? This one is root 3 over 2 and 1/2, and this guy is the flipped version of that, 1/2 and root 3 over 2. Now, all of these guys in the other quadrants share the same reference angles. So what I want you to notice, and this is pretty easy to see, I'm hoping, all the over 3s have the same reference angle. Okay, and all the over 6's have the same, whoa, that was not a good straight line, but all the over 6's also have the same reference angle. Okay, so when you're filling these guys in here, the 150, the 210, and the 330 will all go with this coordinate point here. And then the pi over 3 or 60 with the 120 and the 240 and the 300, they'll all share this point with the exception of who's positive and who's negative. Okay, so now we're just going to finish filling in the unit circle. So I've got negative positive there, I have negative positive there, and then I've got negative negative and negative negative, and then I've got positive negative for both of these guys there. Okay. All right, I'm going to bring myself back. I missed you all. That's the unit circle. Okay. Now, at first glance, when you just look at this slide, this looks super big and scary and intimidating. And what I'm hoping has just happened in the last couple of minutes, if you build it, if you take your time and build it 3 go-arounds so that you're concentrating on the axes, then you're concentrating on the 45-degree lines, then you're concentrating on the 30-degree lines. If you look at it that way, I really, truly believe it's much less intimidating than just trying to look at this and say, memorize it. Okay, so I'm really hoping this helps, but you're going to want to try and build this yourself several times. Okay, you are not given a unit circle on a test, and nor will I ever ask you to build one. I want to make that clear too. This that you see is not a direct curricular outcome of 30-1. What's a direct curricular outcome is for me to say, hey, tell me what the cos of 135 is. Okay, so the unit circle is a tool that we have to help us get to those answers rather quickly once we understand how the unit circle works. Okay, all right, so let's try to practice that then. Determine the exact values of some of the following. So cos of 3 pi over 4. Well, I'm just going to go right to 3 pi over 4. I know I'm in the second quadrant if you can't find it. And I know that I'm looking for the x value. So I'm just looking at what's the x value at 3 pi over 4. And you should be getting negative root 2 over 2. Okay. The sine of 11 pi over 6. So again, 11 pi over 6 is right on my unit circle. It's in quadrant 4. Really close to 12 pi over 6, right? And 12 pi over 6 would be 2 pi. So then I'm reading the y value off of that, and you should be getting negative 1/2. Everybody doing okay? It's so fun. Okay, the tan of 5 pi over 6. So for the tan, remember we're going to go y divided by x. We're going to go sine of theta divided by cos of theta. You'll also notice in the unit circle, every coordinate pair I give you has a common denominator. So when you have a common denominator, you just have to go the numerator divided by the numerator, okay? So I end up with 1 over negative root 3, and 1 over negative root 3, I have just rationalized that to be negative root 3 over 3. That's where that came from, okay? I didn't specify to rationalize, so if you wanted to write that as negative 1 over root 3 like that, that's totally fine, okay? Okay, cotangent of 4 pi over 3. So we have to go to 4 pi over 3. That's just after 3 pi over 3, right? So you should be in the third quadrant. Cotangent is the flipped version of tan. So if tan is y over x, cotangent is x over y. Okay, so I'm going to find that coordinate pair, and I'm just going to take the x value and divide by the y value. So that's going to give me negative 1/2 divided by negative 3 over 2. Because I have the common denominators here, I just go negative 1 divided by negative root 3, and I get positive root 3 over 3 there, or unrationalized 1 over root 3. Okay. Okay, tan of 11 pi over 4, heading over to 11 pi over 4. Now, 8 pi over 4 would have been 2 pi. So what I want you to understand here is I've gone more than a circle. Now, that doesn't mean I'm off my unit circle. It just means I have to work with the principal angle, okay? We've already talked about principal angles. So do you agree with me that 8 pi over 4 right now is the same as 2 pi? When I want to get to a principal angle, I subtract full circles until I can't subtract full circles anymore. So 11 pi over 4, subtract 8 pi over 4, because that's what 2 pi is. That's going to get me down to 3 pi over 4. So the principal angle here is 3 pi over 4. Asking for the tan of 11 pi over 4 is the same as asking for the tan of 3 pi over 4, because 11 pi over 4 and 3 pi over 4 are coterminal angles. Okay, so now I go to 3 pi over 4 and I go sine divided by cos, sine of theta divided by cos of theta, and I get -1. Okay, cosecant of 2 pi over 3. So I head to 2 pi over 3. I remember that cosecant is the flipped version of sine. So if I can find the ratio for the sine of 2 pi over 3, which I can because it's the y value at 2 pi over 3, I just flip it. Okay, so the sine of 2 pi over 3 was √3 over 2. So the cosecant of 2 pi over 3 is 2 over √3. I just flip that ratio. Okay. Then I rationalized it. Again, it doesn't matter which one you have it as. I'm showing you both so that you're comfortable with both. I would accept either one if I didn't specify that I need you to rationalize it. Okay, sine squared of 5 pi over 6. Now, there's a couple things we need to talk about here. First of all, we need to talk about where this square is and what that means. Okay, this is always how it's written. It'll say sine squared of the angle. But what it means is this. Okay, so what it essentially means is you need to figure out the sine of the angle. You take that ratio and you square it. Okay, so it means this. So I'm going to figure out what the sine of 5 pi over 6 is first. The sine of 5 pi over 6 is a half. And all I'm doing there is I'm going to my unit circle, I'm going to 5 pi over 6, and I'm reading the y value. And then a half squared is a quarter. Okay. Okay. Tan of pi over 2. So I'm heading to pi over 2 on my unit circle. Okay. And I'm looking at sine divided by cos. So my y value divided by my x value, that's going to be a 1 over 0. That's undefined. Okay. And so your answer here has to be undefined. Okay. Tan ratios don't exist at pi over 2. There's one other spot they don't exist on the unit circle. Can you find it? If you answered 3 pi over 2, you're correct. Okay, determine the exact measure of all angles that satisfy the following. Draw a diagram for each. So sine of theta equals -√3 over 2, and I'm going from 0 to 2 pi. So I'm speaking to you in radians right now, which means you have to speak to me in radians. I have a negative sine angle, so that tells me I'm heading down to quadrant 3 or 4. So I can figure out the reference angle. I can put that in the quadrant 3 and 4, or I can look at my unit circle for a y value that is -√3 over 2 in quadrant 3 or 4. Okay, either one will get me there. So I have, because I want to be very, very careful that I'm communicating to my favorite math teacher and showing my work, I have created here's my reference angle, okay? If you wanted to just use your unit circle here, like I'm thinking about written response questions on a diploma, you would have to communicate somehow what you're doing with your unit circle. So you would say, I'm using my unit circle. I know I'm in quadrant 3 and 4. I know the y value is my sine. Like you'd have to tell me all of those things if you were just using your unit circle. So it's probably easier to show that you're finding the reference angle and placing that reference angle in quadrant 3 and in quadrant 4. So I need to make sure, now where I'm actually going to use the unit circle here, although I'm stating that I'm trying to figure out the reference angle, I can use the unit circle to get the exact value, because my calculator is only going to give me, if I'm in radian mode, my calculator is only going to give me a decimal approximation, right? So I know based off my unit circle that the reference angle is pi over 3 here, okay? If I had just done that in my calculator, I would have gotten some decimal approximation, and I might not be sure that that decimal approximation is exactly pi over 3. So that's where the unit circle will come in handy for these questions, okay? Okay, so now if I have pi over 3 here, I need to go pi plus pi over 3, so that would be 5 pi over 3. Remember, pi is just 3 pi over 3 right now, right? Sorry, I said 5 pi over 3. I was thinking about the next guy. 3 pi over 3 plus 1 pi over 3 is 4 pi over 3. And then the next guy, I got a little ahead of myself, sorry, would be 2 pi minus pi over 3. So that's like 6 pi over 3 minus pi over 3. So that would be 5 pi over 3. So my two answers are 4 pi over 3 and 5 pi over 3. Okay, okay, next guy. Similar question. We're just going to keep practicing this for a little bit. Tan of theta equals 1 in the domain 0 to 2 pi. So if tan of theta equals 1, things I know is that tan has to be positive. I know tan is positive in quadrant 1 and in quadrant 3. And I know that if it equals 1 and I'm going sine of theta divided by cos of theta, I'm looking for a ratio where sine of theta and cos of theta are the same thing. Because if I take two numbers that are the same and divide them by each other, I'll get a 1. That's at pi over 4. So essentially I have a pi over 4 reference angle in quadrant 1 and in quadrant 3. Okay, so for my quadrant 1, my answer would be pi over 4. And then for quadrant 3, my answer would be pi plus pi over 4. This time I'm going to call pi 4 pi over 4, right? Because I'm just trying to get a common denominator. And so 4 pi over 4 plus pi over 4 would be 5 pi over 4. So my answers would be pi over 4 and 5 pi over 4. Okay. Okay. Cos of theta is root 2 over 2 in the domain negative 360 to 360. So now I've gone beyond just one complete spin of a unit circle. Okay. That's fine. All I need you to do is pretend that you are in just 0 to 2, or sorry, 0 to 360. Okay. Always do these questions pretending you're 0 to 360 and then add in coterminal angles that match your domain. So if I'm looking at cos of theta equals a positive number, cos is positive in quadrant 1 and in quadrant 2. And so I'm looking for a reference angle. The reference angle that matches root 2 over 2 then would be pi over 4. So I have pi over 4 in quadrant 1. I have pi over, sorry. See, I just did what I told you not to do. I need to speak in degrees right now because I was spoken to in degrees. So let me change that conversation and say 45 degrees. The reference is 45 degrees. So I have a 45-degree angle in quadrant 1 and a 45-degree angle in quadrant 4. Okay, so then I'm looking at in quadrant 1, I'd have 45 degrees. But then I also want to get a coterminal angle. So the coterminal angle, I just subtract 360. And that gives me negative 315. In quadrant 4, this would be positive 315 because I'm going 360 minus. And then to get the coterminal angle, I'll go subtract a circle from that guy and get negative 45. Okay, so what I need you to see here is that these guys are the same angle. They both represent this. One of them looks like this, the 45 degrees. The other one essentially looks like this, okay? And I'm allowed to do that because of my domain. My domain allows me to go from negative 360 to positive 360, okay? This guy, the first one is this green rotational arrow that I did. Okay, but then to get the coterminal angle, I'm subtracting, that was a really bad arrowhead. To get the coterminal angle, I'm subtracting 360 from the 315, and that gives me negative 45, which is this space right there. Okay, and so my conclusion is actually plus or minus 45 and plus or minus 315 degrees. Now, what I worry about when I write this conclusion is I don't want you to think that they're always going to be like the positive and negative versions of each other. It actually had nothing to do with that. And what I want you to notice is the 45 did not go with the negative 45. It just worked out that way based on the two quadrants that I had. The 45 coterminal was negative 315. So don't, please, please, please don't assume that as soon as I allow you to go negative, you just put plus or minus on everything. That's not how it works. You need to map it out to actually see what's going on, okay? Okay, hopefully that's clear. Now let's try secant of theta equals 2. Now, if secant of theta equals 2, secant's the flipped version of cos. So instead of looking at secant of theta equals 2, I'm just going to change that to cos of theta and flip the ratio. So saying secant of theta equals 2 is the same as saying cos of theta equals a half, okay? So for cos to be positive, I'm in quadrant 1 or quadrant 4. I need to try and figure out a reference angle. So I know that the reference angle will be the inverse cos of a half. And I know that that's a 60-degree angle. So I know I have 60 degrees here and 60 degrees here, okay? So again, I'm allowed to go from negative 360 to 360. So I'm gonna do the same thing that I did on the last slide. So this guy is 60 over here, but to get my coterminal angle, I know that that's 60, so then I'll subtract 360 from it, and I know the coterminal angle would be negative 300, okay? This guy here is my 300. The coterminal angle will be 300 minus 360. I'll go back a full circle, and that will leave me at negative 60, okay? So the same thing happened here, and it's partly because I'm dealing with cos as a positive. But again, I don't want you to look at, oh, it's 60 and then it's always negative 60. It's not, okay? Please don't think that. Okay, but for this guy, my answers are negative 300, negative 60, 60, and 300. Okay? All right. Now, last question for today. 2 points are drawn in standard position as shown. Determine the measure of theta to the nearest degree. So there's lots of different ways you could do this. But I would want you to see that both of these points that I gave you are points marked on a unit circle, okay? So right away, I know that there's a 45-degree reference angle right here, okay? Or I could say right away, I know that that's 135 degrees right here, right? If I did this, that would be 135 degrees, okay? I know that root 3 over 2 comma 1/2, that would be a 30-degree angle, okay? The other thing to notice here then is these things are never drawn to scale, okay? If you compare the 30 degrees with the 45 degrees, the 30 degrees actually looks like a bigger angle on paper. You can't use your judgment of your eyes here. It's meant to just work with the math, okay? Okay, so if I want the pink theta there, either I could go 135 minus 30, or some kids like to go 180, because I know this whole thing here is 180 minus the 2 reference angles. It doesn't matter, you're going to get the same answer either way, okay? So no matter how you look at it, you should get an answer of 105 degrees, okay? All right, so that's it for today. I know this was heavy. This was a lot going on, and you might want to watch this a couple of times before you start getting comfortable with it. But this is the homework to try. And please come see me if you have any questions. I would love to help. You know how much I love trig. It's the best time ever. Okay, have fun, and we'll talk soon. Take care.